Good morning, friends. Welcome to the session on spatial sampling designs and spatial data analysis. We have 5 speakers, and it is good that all 5 are present. Good representation from the across the globe. We can see the 3 countries are participating as presenters: India, Philippines, and Spain. And best part is that our gender participation. There are 3 female presenters and 2 male presenters in this session. Therefore, that takes care of gender inequality. Without taking much time, because 5 speakers are there, we have 90 minutes. Therefore, may I request the speakers to take around 13 to 14 minutes each, so that we have 2 to 3 minutes for discussions. And at the first, I'm inviting Dr. Anna Christian from Asian Development Bank, Philippines, to make her presentation on improving paddy rice statistics using area sampling frame techniques.
Okay, so thank you very much, Mr. Chair, and good morning, everyone. So this morning, I'd like to talk about a project that was conducted by the Asian Development Bank in 4 pilot countries, the Philippines, Thailand, Laos PDR, and Vietnam. And it's on improving paddy rice statistics using area sampling frame technique. So I'll just quickly go over the outline of my presentation. I'll have a brief introduction, and then I'll go directly to the methodology, the sampling frame approach for pilot rice crop cutting survey. And then I'll also discuss about the objectives of the study, enumeration based on area frame, the stratification that we use, the sample design for the pilot survey, and also the methodology we adopted for the crop cutting, rice area estimation, weighing procedure, and then finally, comparison of results and conclusions and some recommendations. So we all know that timely and reliable crop production and area estimates is important to monitor government development plans to mitigate the effects of extreme weather and climate change. So there are 2 common methods adopted for compiling agricultural statistics. One, the administrative records, and also through field survey. So the starting point for field survey is a sampling frame, which is using either a list or an area frame. So we recognize the potential advantage of using area frame. The completeness of frames can be guaranteed by specifying the geographic boundaries of the study area. So this study aims to pilot test the area frame approach for estimating paddy rice area, production, and yield for the 2015 cropping season in pilot provinces of 3 countries, in Savannakhet in Laos PDR, Ang Thong in Thailand, and Tai Binh, Vietnam. We also conducted this study in Nueva Ecija in Philippines, but unfortunately, we had a strong typhoon in October. During the harvest season, it was impossible for us to do crop cutting. So for this study, we also only considered the 3 pilot areas. Also, it aimed to compare direct estimates of total rice paddy area, production, and yield from 2 methods. First one is involving the measurement of plot size using a GPS instrument. The second one is to utilize a digitized map or farmer-identified plot boundaries on a high-resolution Google Earth image. And then a third method of obtaining ratio estimate based on independent mesh-level measures from digitized Google Earth map. And then finally, to compare the results with existing administrative data. So, as we all know, area frame is defined using satellite images that are stratified into different categories related to the concentration of rice growing area. So for our study, our primary sampling unit, or PSU, is a 200 meter by 200 meter square mesh, as you can see on the screen, which is spatially defined on a digitized satellite image map. So this sums up the methodology that we adopted for sampling using area frame approach. The first one is we define the area frame using segments. So we identify the boundaries of the pilot areas that we have identified. The second one is the land classification by land use using remote sensing data. So we categorized our sample meshes into 4 stratum. So we had 4 strata were defined according to the concentration of rice growing areas. So for this study, we use the Erie paddy rice map of 2015 using optical MODIS data, and also land cover map from the European Space Agency under their Globe Cover initiative. So this one uses 2009 Landsat data to classify the area according to land use. So what we did was we overlaid 2 layers of map, the MODIS paddy rice area from the International Rice Research Institute, and then the Globe Cover map from the European Space Agency. So using these 2 maps, we identify the rice growing areas. We randomly select sample meshes from this stratum, and we identify this stratum as the high probability stratum. And then the second stratum, the Erie, the medium probability stratum. So these are the areas which are identified to have paddy rice planted based on the Erie rice map alone. And then the third one, the Globe Cover, which is the low probability map. These are the areas identified by the Globe Cover land use classification map. So as you can see, it can be planted to rice, but it could also be planted to other forms of vegetation. And then finally, we have identified the 4th stratum, which is the other stratum. This is a very low probability stratum because these are areas which are identified by both maps as maybe either commercial space or residential area or areas with other infrastructures. Basically, these are areas where we do not expect to find any rice planted. So this is a very low probability stratum. And the next one is the selection of segments per classification stratum, or PSU. So again, our PSU is a 200 meter by 200 meter square mesh, which is spatially defined on a digitized satellite image map. And then the next one, listing of plots partially or fully within the PSU. So for this step, we really rely on on our enumerators, which are mostly staff from our implementing agencies. And then finally, the random selection of plots for enumeration or crop cutting. So this is the distribution of meshes by stratum for each pilot province. So you'll notice that we have around 562,000 square meshes in the province of Savannakhet, which is significantly bigger than the 2 other provinces. So we have fewer sampling meshes in Ang Thong and also Tai Binh, Vietnam. Okay, so sample size and allocation. So stratified random sample of 120 meshes were selected for the pilot survey in each province. So these sample meshes are randomly selected, and for all these pilot provinces, we also have allotted reserve or replacement meshes for very rare occasions where we have to replace the mesh for maybe due to some accessibility or security issues. And then the sample allocation concentrates samples in strata with more rice. So as you can see, we have more sample meshes in the Erie Globe Cover stratum because that is the stratum where we expect to find more rice planted area. Okay, so we utilize a stratified 3-stage sampling design. The first stage is the selection of sample mesh within each stratum. The second stage is the random selection of 4 sample plots with rice within each sample mesh. And then the third stage is the random selection of 1 subplot within each sample rice plot for crop cutting. So to explain that further, so this is the weighing procedure that we've done for this study. So the first stage probability of selection, where your P is the first stage probability for each sample mesh, your N is the number of mesh selected for each stratum, and your big N is the total number of mesh in frame for stratum H. So to explain that further, so this is the map of Savannakhet Lao PDR. So you see that I think the images of the squares is a little bit small, but we divided that area into 200 meter by 200 meter square mesh, and we stratified them according to land use. So the green one are those areas identified to have rice. This is the high probability stratum, which is the Globe and then Erie Globe Cover stratum. And then the blue ones, the globe cover, Erie, and then others. And then this is also the map of Ang Thong, Thailand. This is the area, the surface area is smaller, so you can see now the square meshes. This red dots denotes the sample meshes, the 120 sample meshes that we've identified for Ang Thong, Thailand. And then finally, Tai Binh, Vietnam. So if you look closely at the maps, you'll see that Savannah Cat has other forms of land use within the area. So, and then compared to Ang Thong, Thailand and 2 minutes, okay, sorry. So then the second stage probability, I'll go quickly because I only have a few minutes left. And then in each sample mesh, we identify all the areas which have rice planted in them. And then for the third stage, finally, after identifying all the rice plots within the mesh, we identified randomly a 2.5 by 2.5 meter subplot for the implementation of crop cutting. Okay, just a review of the crop cutting method that we've implemented. So first, we selected randomly the 120 sample mesh, and then the random selection of plot within the mesh, tracking of plant boundaries, and then the random selection of subplot, and then we did all the usual harvesting and post-harvesting procedure, what the farmers would usually do with their harvest. We have threshing, cleaning of sample, moisture reading, drying, and then finally weighing and reading the moisture content. Okay. So this is the final distribution of sample meshes with rice by province. So in Vietnam, we have a total of 72 meshes out of 120. So these are the areas planted to rice. In Ang Thong, we have 66, and in Savannah Cat, we have 78. So as mentioned earlier, for rice estimation, we did 3 methods. The first one is the unmodified tracts, which are area estimates based on actual tracts recorded by the enumerators during crop cutting. So after randomly selecting the 4 sample plots within our PSU, we requested our enumerators to walk along the boundaries of the sample mesh using a GPS device. And then the second one, if you notice, this is almost similar to the first image, but this one, you'll see that the lines are more straighter compared to the first one. Because we realized that during field implementation, sometimes it's not the GPS device, while we consider it as a more accurate way of measuring area, we realized that in the actual field implementation, sometimes it's almost impossible to walk or get or capture the actual size of the plot. So what we did is we used high-resolution Google Earth images to digitize the plots previously recorded with the enumerators. And then finally, rice area estimation at the mesh level. So for this one, we asked also the enumerators to bring with them printed maps. So when they reached the mesh, they recorded all the rice, all the areas planted to rice, and then digitized that again using Google Earth. But for the first 2 methods, we only randomly selected 4. But for this one, for the third method, we considered all the rice areas planted to rice. So the first image is the printed map, and then the second one is the digitized map using Google Earth. And then for the rice area estimation, we just like to inform everyone that we use QGIS, an open source GIS application that provides viewing, editing, and analysis capabilities. Okay, so I'll go straight to the results of the study. So we compare the area estimates that we gathered from the 3 methodology and then compare it with official statistics. So as you can see, so the first 3 bars are from the experiment that we conducted. So you'll notice that this is for Savannah Cat Lao PDR, by the way. You'll notice that the other stratum, which is the very low probability stratum, even though we only have 2 sample meshes found to have rice in that stratum, has a huge implication in the total area estimation. Okay, so the official statistics is also comparatively lower than the other 3 rice area estimates. And for Ang Thong, Thailand, the case is different. The official statistics is higher than the estimates we got from using the 3 methodology. And also same with Tai Binh, Vietnam. And also for the comparison of field, So these yield estimates are standardized at 15% moisture content for Savannakhet. That is the standard moisture content according to the farmers, and 14% for Angtong and Taibin. And while the official statistics are based on the published official statistics of the Center for Agricultural Statistics in Lao PDR, the Office of Agricultural Economics in Thailand, and the General Statistics Office of Vietnam. So you'll notice that in all three provinces, the official statistics, the yield are much higher than the estimates we got from this experiment. And just to conclude, we found that there is a need to improve the stratification based on most recent and higher resolution satellite imagery, given the number of sample meshes without rise in the Erie and globe cover strata. So the use of Sentinel-1 and Sentinel-2 are both promising. Maybe the reason why is because during that time, the only available free satellite image that we have is from the Globe Cover Initiative, which is from 2009 Landsat land cover classification. So we might have to use, or for future study, we might consider using other free satellite data of higher or more recent resolution. So the rise found in two sample meshes of the other stratum in Savannakhet also indicates that there is a need to improve the stratification. So as I've mentioned earlier, although we only have two sample meshes from the other stratum, it has a huge implication in the total area estimation for the area. Also, the large variability in areas of plots inside the mesh increases the sampling errors. So in all pilot countries, we noticed that there is a large variability of sizes. Say within the 200 meter by 200 meter mesh, it's around 4 hectares in area, but you can find some farms are 2 hectares in size, while the others are just maybe 6,000 square meters or 0.6 of a hectare. So that's how variable the sizes are within the sample mesh. Also, mesh-level digitization significantly improves precision of estimates of total area of rice paddy. Also, we observed that ratio estimation improves the precision of estimates of total production of rice. And also, this project wouldn't have been possible without the help, a tremendous help and effort from our implementing agencies, because as you know, ground truthing or validation is very important to verify information derived from remotely sensed data. And the deviation with official statistics for rice area and yield could be due to the presence of non-sampling errors, subjective intervention, and political leadership at the local government levels. So we just want to inform you that after the implementation of this project, we gathered all stakeholders in each pilot province to do a dissemination workshop. And from there, okay, just to wrap up, at least the pilot countries are cognizant that there are weak points in their administrative data collection system. So they know that there are really some points or some areas that need to be improved. And then finally, the use of remote sensing and GIS technologies to obtain rice area and production estimates with relatively high precision is a major benefit for this methodology compared to the existing admit data collection system in pilot countries, for which measures of precision are not publicly available. So this work is published as an economic working paper of the Asian Development Bank. So at this point, I just quickly want to acknowledge the presence of two of my co-authors in this room, Ms. Pamela Lapitan and Mr. Nagraj Rao. You can take a look at the publication to know more about the details of the study. So thank you very much and good morning.
I think we hold questions for the last 4 hours speakers. Now I invite Dr. V.K. Saigal, who is Principal Scientist and Professor at the Indian Agricultural Research Institute. He will be speaking on spatio-temporal analysis of paddy and wheat residue burning in North India during 2018-19 using satellite remote sensing.
Thank you, Dr.
V.K., please be brief and within time.
Thank you very much. As you know, we are all lucky that you are visited Delhi when at least winds are favorable to us and you are not really feeling the heavy load of pollutants in the air. But few days back, the situation was bad, and one of the reasons which is attributed to this is burning of crop residues in our neighboring state of Punjab and Haryana, covering all this area, bringing it a lot of pollutants, especially PM 2.5 particles. And We actually are a Preems lab at the Division of Agricultural Physics at Indian Agriculture Research Institute. And the preamble is that for last 50 years, our focus of whole agriculture research system has been increasing production. But we have never thought of what is going to happen to the residue which we are going to produce. So we are producing something like 300 million tons of food grains, but dry biomass is double the amount of that, 682 million tons. And we have estimated for 11 major crops across India in 3 seasons using ground surveys. And we found that there is at least 178.7 million tons of residue, which is surplus, is of no use by anyone. And especially 72% of that is coming in our main Kharif season, which is coinciding with the monsoon, and 27 is from our winter season, that is Rabi. And major 2 crops, rice and wheat, they contribute more than 50% of the residue which is produced, and this is the distributions of total annual dry biomass and surplus biomass across India. So anyway, if you have to do any decision in managing these residues, you need to make decisions, and you can't manage what you can't measure. So you need observations, and satellites are one of the measures to know where all the residue is produced and where all their burning is happening. So actually the government of India implemented 2 years back a centrally sponsored scheme to manage in situ crop residue management, and they had a very, very difficult task in the sense they wanted to judge the success of the scheme. So they approached our lab and they said that why don't you monitor residue burning events and map the area and pollutants which are coming out of that, and how does it do? The good thing is that we have a satellite ground station with us, and we receive these all types of different satellite data which have middle infrared and thermal infrared data which can actually measure the temperature of the land and detect the fires. So for the 3 states of North India, Haryana, Punjab and UP, we measured this throughout the season during last year. So there was 2 type of things which we did. Thermal remote sensing using coarse resolution, multiple passes daily data from 7 satellites, and then finally to map the area we used multispectral high resolution at 20 meter Sentinel-2 MSI data using pre-burning crop status and post-burning crop status to map the area. And this is how the distribution, actually this we did it nearly 61 bulletins we issued daily basis, and this is how the distribution happened across the 3 states, and there were 59,695 burning events in our northern state of Punjab as compared to 9,232 in Haryana and 6,000 in Uttar Pradesh. Of course, there was some issue during 2 days when there was a lot of cloud over the region and we cannot detect using satellites. So that is a drawback of the technology. And this is how the maps were being produced and distributed. These are the final, how the distribution of burning events, each of those points show in the 3 states. And then they were compared how daily cumulatively in that season 2018, actually we are doing for 2019 also, current season also going on. So 2018 versus 17 versus 16 in all the 3 states, and it gave an idea that around 15% and 41% reduction happened in that particular year as compared to 2017 and 16. This year it is still 16% as compared to 2018. So this reduction was less in Punjab, which is contributing mainly to the burning. Haryana was around 30% and UP was around 25%. And how district-wise these events were distributed, they were also mapped between 1 year to another year, all the 3 states, and it showed that where are all the districts where there is an increase or decrease. I don't know if you can see these legends. It shows how much increase or decrease happened with respect to last year. So these daily reports were being shared with the Ministry of Agriculture, which was communicated to the ground level with the district officials to look after that they should take action wherever burning is happening to prevent it. Of course, success depends on many other factors. And it is not only that, satellites also detected the intensity. Intensity tells whether the amount of residue burnt is more or less, and we found that as compared to 2017, in 2018 there was no change in intensity in Punjab. These are high intensity fires, these are low intensity fires. But there was at least 5% change from very high intense fires to very low intense fire in Haryana. So that shows there was though burning do happen, but there was a shift towards partial burning. And this is what district-wise statistics were accumulated, which are the hotspot districts where they need to take action. And this is how in the current season as compared to 2018 has happened till 13th of October. This is an old slide, now it is up to last days. And these are the maps which are being produced. And then the other thing is we mapped using high resolution data where is all the rice and where are all the rice which has burnt. And statistics were generated district-wise, how much paddy area, paddy burnt, how much is the straw produced and straw burnt, and these were statistics generated with a very high resolution data set. And an important thing was that the ministry wanted to know where are all the villages where no burning has happened or very less burning has happened. So because they wanted to go and learn what is the reason that there no burning has happened and there are villages where very high burning. So this kind of statistics were also generated by overlaying the village level boundaries on the high resolution maps to show that there are these many district-wise, these many villages are there which have produced where no burning happened, or these are the number of districts where less than 5% of burning happened. And similar analysis was happened for Haryana also. And because these are two different data sets, one is coming from thermal, another is coming from multispectral, we also did a correlation between whether the burning events versus burnt area do they have, and we found that there is a very high correlation of 0.92 to 0.98 in both the states. So which gives us the confidence. Then we developed also a methodology based on the intensity of fire, how much is the particulate matter and greenhouse gases being emitted from all these burning events. I don't want to go into the science of that here, but these are the estimates which we did it in terms of how much emissions of methane, NOx, CO2, carbon monoxide, particulate matter 2.5 and 10 were generated out of this. So we can calculate the environmental cost depending on all these emissions of pollutants into the atmosphere and how they were distributed across the districts. And this is not only we did for rice, we did it for falling wheat during November to, the season is from November, but this happens, the harvesting of wheat happens between 15th April to 31st May. So as compared to rice, the number of burning events were very less, but in Punjab they were distributed nearly uniformly across the districts. Whereas in Uttar Pradesh, our largest state, there was one district which was contributing maximum 3,774 points. And this is how they were distributed as compared to 2018 to 19. And we find in Punjab, actually there was reduction in number of wheat burning events, whereas in case of Haryana, there was increase in 2019 as compared to 2018, as well as there was a large increase in Uttar Pradesh. So though we always say that our eastern part of the region is deficient of residues, but we are finding that the tendency of going to the practice of increasing residue burning is increasing. And we generated a database. It is hosted on our ICAS data center, and those data has been also linked to a Krishi Geo portal. So all the data of last year to this year till yesterday, all the burning events, what is their location, which district, which tehsil and which village they are, and what is the intensity. These maps you can visualize on these two websites or geoportals. Thank you.
Presentation, we again keep the questions for the end. Thank you very much once again.
Thank you.
Now I invite Dr. Prachi Mishra. She is Principal Scientist at Indian Agricultural Statistics Research Institute, and topic is GIS-based sampling designs for regular and irregular sampling units.
Good morning, everyone. I thank the organizers for giving me this opportunity to present my work. And the title of is GIS-based spatial sampling designs for regular and irregular spatial units. Now, when we talk of spatial data, the real world entities can be expressed in three ways, that is point, line, and polygon. We all know that when we talk of spatial data, unlike attribute data. But then, unlike attribute data, spatial data possess a unique quality of dependence, which actually makes it special. So the unique statistical property of spatial data, that is spatial dependence, needs special emphasis that how the statistical techniques should be modified, whether it is basic or descriptive statistics, or it is spatial designs or designs of experiment. Because spatial dependence means, according to Tobler's law of geography, that all things are related, but nearby things are more related than distant things. So it refers to basically the relationship between spatial units, which actually make it dependent. And we know that as the distance increases, the dependency increases. And this makes it unique. Here there is some maps showing the spatial variability present in the field, and soil distribution maps, which is due to the unique property of spatial data. So the basic point is, earlier the traditional sampling designs which were used for spatial data were the same traditional designs like simple random sampling, stratified sampling, and systematic sampling. And it was used in this way, that is simple random sampling aligned in both directions, or stratified sampling aligned in row or columns, or systematic sampling unaligned in both directions, because no specific designs were developed for spatial data. But as I already mentioned, the problem in these sampling designs, which does not take care of the spatial data, is that they fails to capture the dependency present in the data, which raises alarming questions about the estimators' properties, that is sufficiency, efficiency, consistency, or bias. And therefore, there is a need to modify the classical traditional sampling designs like simple random sampling or stratified sampling or systematic sampling in view of the spatial data. And we all know that dependency in the spatial data is accounted by the spatial correlation. So this proposed sampling design has been developed in order to take the dependency into account using the unique property of spatial data, that is spatial correlation. So basically we have tried to exploit spatial correlation, which shows the dependency in the data. And I'll show you the proposed sampling design, in which we first estimate the spatial correlation and go for the spatial stratification. Then a sample selection design has been developed, particularly keeping into account the spatial correlation. And finally, the estimation procedures are also modified as per our sampling design. So this is the basic methodology. First of all, after completing the database using the GIS, we calculate the spatial correlation, for which basically we need to select the neighbors, and then we go for the spatial stratification, that is by testing the stationarity we go for spatial stratification, we make strata, and then finally we select the sample and get the estimators from them. So without going into details of spatial correlation, we can just see we have positive, negative, and no spatial correlation as the figure shows. And the basic formula for spatial correlation is shown on this slide. And why I'm showing you this is we have this special unique term Wij, that is the neighbor, which is 1 if I and j are neighbors, and is 0 otherwise, which actually captures the spatial dependence in the data. And these can be defined by different criteria, that is diagonal-wise, adjacent, and both diagonal-wise and adjacent, which is the Queen's case, which I have taken in this study. So in the study has been done on the Rohtak district, and this is the village boundary map showing 492 villages or polygons. And here we have first identified the neighbors at various lags. Like we can see the contiguous neighbors in which all the polygons touching the boundary are neighbors, first lag neighbors. Then similarly we can identify the second lag neighbors and the third lag neighbors. And once we identify the neighbors, we can calculate the spatial correlation using the formula which I had shown you earlier. And then after calculating the spatial correlation, we go for stratification. Taking the same map, we start with a small homogeneous group, taking one polygon and all the first lag neighbors with it. And then using this formula, we go on testing for each polygon, whether it is included in that homogeneous group or not. And in this way, we go on and on, testing for each individual polygon till we get a homogeneous group. So in this way, we divide the entire district or polygons into different groups. So this is the formula which we have used. So here beta is the spatial correlation for ith polygon, and beta cap is the mean of the spatial correlation. And coming to the sample selection, which is most important, which highlights the spatial property of the sample. So this, the basic principle behind the sample selection is that the probability of selection of any unit increases as the distance from the area already sampled increases. So the basic logic behind this is that nearby units gives us the same information, and as we go far away, we get different information. So if we are selecting units nearby, then we are at loss in two ways. One thing, we'll not get more information regarding this, and secondly, cost will also be more. So according to the principles of sampling design, we are selecting this sample. So in this, the first unit is selected by simple random sampling, and then for selection of second units, we have calculated the weights, which takes into account the spatial correlation. In the sense, weight for second unit is 1 minus beta D12, where D12 is the distance between the first selected unit and all the remaining units. Then next one, once the second unit is selected, then we take care of the all other selected units. Now the basic uniqueness in this sampling design is that selection of sample of second unit is based on third, and again for third unit we are taking care of both first and second selected units. I'll show you by this figure. I think it will be more clear. So here you can see that first unit is selected at random, then we calculate this distance from all the remaining 491 polygons and calculate the probability, whose weights is based on the spatial correlation. Whichever has the highest probability will be selected. Once two units are selected, then in the second figure you can see here, then in this figure you can see here that all other selected units will take the distance from first as well as the second for the third unit. So again in the next step, we will have 3 units selected in the sample, and selection of fourth unit, we will see the distance from first, second, third earlier selected unit. And therefore, the probability of selection is changing after each draw, that is after selection of each unit. So this is unique in itself, the sample selection process, and this takes care of the spatial dependence in the data. Then we have the estimation procedure again, which is based on, in which we are including the here this weight. So in this, the probability alpha n, we are including the spatial coefficient here in UN, as well as the distance. This is xn is the distance measured from the 2 units. So this is, in a nutshell, the methodology which has been developed, that is the spatial design, and this is the variance. And in this way, we have proposed 4 sampling designs, that is contiguous unit-based spatial sampling. Then same thing is done on stratified basis. First we make the strata and then we apply the same technique, which is stratified contiguous unit-based spatial sampling design. And then also we tried modifying it, because here the first unit is selected by simple random sampling, but in modified case, just to see the variation, we selected the first unit by PPS, that is probability proportional to size unit. And then similarly, for modified, we have stratified modified contiguous unit based spatial sampling. So this is one case. Coming to next, okay. Then the study area here we had taken the Rohtak district, and the character under study was irrigated area, and the auxiliary character was cultivated area. So the spatial correlation actually is calculated on the cultivated area, and the irrigated area is estimated. These are the results for different sample size, and we can see the efficiency of modified, stratified modified cubs is highest as compared to other techniques, and we have compared these techniques with the other traditional techniques also, like simple random sampling with replacement, without replacement, stratified simple random sampling without replacement, dust, and stratified dust. So these are for different sample sizes. This is the efficiency relative bias which has been plotted. And next, coming to the problem of irregular area units, because in India and many other developing countries, we have villages and districts which are irregular shaped, unlike the developed countries, and which really we have a lot of problem because of this. And again, this contiguous area units may not work very efficiently in case of irregular area units, because the problem is variation in shape and size, edge effect and boundary effect comes into picture, and it makes it multidimensional. Now the issue is how to solve this problem. So we tried to change the neighborhood criteria here, and we calculated the modified spatial correlation coefficient, and instead of using contiguous neighbors, we used distance-based neighbors here, which does not account for the shape and size of the units. So here you can see we have opted for distance-based neighbors. So here if you can see 3 colored circles, we have the first lag neighbors, the second lag neighbors, and the third lag neighbor. So we have to adjust for some optimum distance. Here we have taken the distance for which the spatial correlation is maximum according to the data at 20. So this is the area, this is the radius of the circle which we have taken, 20 units for the first lag spatial correlation, and then for the second lag 40, and then for the third lag 60. So in this way we calculate distance-based neighbors, and using the same sample selection method and the estimation procedure, we have got the estimates. And similarly, on consequently our contiguous area unit spatial sampling, we got distance unit based spatial sampling technique, then stratified distance unit based spatial sampling, and again modified, in which in first case we have selected the sample using probability proportional to size, that is PPS, and stratified modified distance unit based spatial sampling technique. 2 minutes, okay. And this proved to be better than even cubs. So this is the graph of the coefficient of variation, relative efficiency, and of various estimators as compared to other ones. And similar study was conducted using remote sensing as auxiliary variable, as pointed in the plenary session also, that remote sensing can be used as auxiliary variable. So for estimating the area under wheat crop, we used NDVI as auxiliary variable and calculated the spatial correlation on the basis of NDVI data. For all the villages, we got NDVI values, So earlier we were using irrigated area. Now for NDVI values, we calculated the spatial correlation, and using the same sample selection method and then the estimation procedure, we calculated the area under wheat crop. And this is the methodology. This is very common, which we use. This is all remote sensing methodology, classification of image, and then NDVI and estimating area under wheat crop, and then this one, and then using our stratified cubs and stratified dubs, which were based in the earlier techniques. And this is the comparison of the various techniques. That is, area under wheat in that year was reported as by simple random sampling as 132, then stratified cubs, stratified dubs, and traditional remote sensing techniques. So we had very low relative bias for stratified dubs, followed by stratified cubs. That is 1.02 and 3.87, and then the remote sensing technique, and then simple random sampling. So the basic conclusion of this study is that if the data is spatial in nature, we should not use traditional sampling techniques like simple random sampling, stratified and all, because it fails to capture the dependency in the data, and we can exploit the unique spatial correlation and other variables of which are spatial in nature, and accordingly use the spatial, develop spatial sampling designs. Thank you.
Thank you, Dr. Prachi. Now I invite the next speaker, Dr. B.N. Mandal. He is working at Indian Agricultural Statistics Research, New Delhi. He will be speaking on distance balance sampling plans useful for sampling from naturally ordered populations.
Thank you, sir, and good morning to all of you. The the topic of the title is distance balance sampling plans, which are useful for sampling from naturally ordered populations. This work is a part of a PhD program under which I have done under the supervision of Professor Rajendra Prasad. In sample surveys, one important decision that the surveyor has to make is the choice of a suitable sampling design. And while choosing a suitable sampling design, there are many factors that has to be taken care of. One of them is the nature of population that is being surveyed. So here in this study, we consider the population which are naturally ordered. That means there is some natural ordering of the units. Maybe that may be because of the space, or maybe because of the time, or like that. And under that ordering, naturally ordering, it is expected that the population units which will be surveyed, they are similar when the units are nearer. So because of the that natural ordering. Now, for example, consider sampling of plants from a field to know the intensity of damage done to a crop by pests. Now, if the because the crop is planted in rows, so nearby rows will be affected by the pest. So the measurement of the pest intensity will be similar in the nearer rows. So it is quite natural in this case that if you select a row, then in a sample you should avoid the nearer rows, because that will give the similar kind of pest infestation data. SRSWOR, simple random sampling design, if you select for such a survey for such kind of population, then it will not be a good plan, because it will be it can give a sample which has nearer units in the sample. So, but that is not desirable in this case. So, some alternative sampling design has to be used. So, other examples also might be there. For example, say estimation of toxicity level at a toxic waste dump site, or estimation of maybe potato production in a field like this. So in all this kind of populations, the nearer units will be giving similar measurements, and it would be desirable that the nearer units are avoided. So one such sampling plan which was suggested is that the balance sampling plan excluding contiguous unit, which were introduced by Hedayat et al. In 1988. In these plans, the property is that chance of inclusion of any contiguous pair of units, they will be 0 in a sample, and the which are non-contiguous, their chance will be constant. So inclusion probability for the nearer units will be 0, and non-nearer units, that will be a constant value. So that's why it is called balanced sampling plan, excluding contiguous units. And here the contiguous definition means if the units have a distance of 1. Suppose the distance, say a distance 2 units, if they have distance 1, they are contiguous. These were later on extended to a class of plans which are called balanced sampling plan avoiding adjacent units, that is BSA plans. Here they considered the avoidance of more than distance 1 unit, that is not just contiguous but also adjacent units, say up to a certain distance. But there was a problem in these plans, that it is that they do not provide any unbiased variance estimation for the, say, Narayan Hurwitz Thompson estimator. That was a problem in this plan. But though they provide unbiased estimation of the total, but variance estimation was a problem. So because of that, in this study which we undertook in the PhD program, we introduced a class of sampling plans that are called a distance balanced sampling plan, and they retain the desirable property of this BSA plans, but also permit the unbiased variance estimation. That was the main advantage of this plan. So the definition is that a distance balanced sampling plan is a sampling plan in which the all pairs of units which are having same distance from each other, they will have the same second order inclusion probabilities. That is the main advantage, and that's why it is called distance balanced. And the second order inclusion probabilities are also non-decreasing, because as the distance will increase between the units, their chance of inclusion should increase. That's why there is a non-decreasing function of the distance between the units. That should be the property, and this is the definition. So for example, to illustrate it, if suppose you have the distinct unit I and j, and their distance is suppose, and there are two other pair distance, say k and l. So suppose the distance between I and j is more than the pair of units k and l, then pi ij, the second order inclusion probability of the unit I and j, will be more than or equal to the second order inclusion probability for k and l. That is the, and the pi ij will be constant for all the I and j which are at same distance. Okay, that is the main property of this sampling plans. So now for estimation, consider that the population has n units, capital N units, and the sample size has small n. That number of units have to be drawn. Then for the development of the theory, we worked under a particular assumption. That assumption is that the units are arranged under circular ordering in a one dimension. But this assumption is needed for the algebraic simplicity, but this can be extended for other kind of scenarios like in 2 dimension or in general scenarios. But in this study particularly, we worked under this assumption. So here is the specification of the, suppose this there is a population of 10 units. Yeah. So arranged on a circle. These are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. These are the 10 units. Pardon me for the figure, it is a hand-drawn image. So the distance between the unit 1 and 2, that is 1, and 2 and 3, 1. Similarly, 1 and 3, the distance is 2. Likewise, and the distance between 1 and 10, unit 1 and 10 is 1, 1 and 9 is 2 because of the arrangement. So we assume these are the contiguous, these are likewise the distance are measured. Okay, so the distance between, in theory, the distance between the two units I and j can be measured by this quantity delta ij. That is the distance, and that will be given by this formula. So minimum value of the absolute I minus j and n minus I minus j. Out of this, whichever is the minimum, that will be the distance between the unit I and j. And the possible values for a circular ordering, the delta ij can take for a population of capital N, they can take the values 1, 2 up to capital N by 2 modulus value. Okay, so that is the value. So these are the possible values that delta ij can take. Now, for deriving the values of the pi ij's under this population, under this sampling plan, the pi ij is given by, suppose, this formula gamma and the function of distance between I and j. So, and if we keep the constraint that pi ij, because they are inclusion probabilities, so it is lying between 0 to 1. So we have to find the value of the constant gamma. So we can, using some algebra, we can simply get pi I is equal to summation of fij gamma upon n minus 1. And then if we assume that if we want all the inclusion probabilities to be equal, say small n upon capital N, then we can easily derive that pi I j will be this will be given by this formula. Now, since the pi j's depend on the choice of the distance function between unit I and j, so choice of the different choice of the Fij will lead to different sampling plans. So DBSPs are a class of sampling plans. It includes many member sampling plans, such as if it is constant, Fij is f, say value, so then it will be result to simple random sampling without replacement. And if we assume that it is 0 for certain distance m and it is constant for distance between above m, so then it will lead to a BSA plans. So these are it is a bigger class of designs compared to the BSA plans. And one example of such a plan is, suppose this is a example, say population size 5, sample size 3. So these are the possible samples in the sample space, and these are the probabilities of selection for each of the, and you can see in this sampling plan, if you obtain the values of the inclusion probabilities, you will find that the first order inclusion probabilities are 3 upon 5, and the second order inclusion probabilities for all the pairs of units which are at a distance 1, say 1, 2 and 2, 3, these are all at distance 1, the units, they will have the inclusion second order inclusion probability 1 by 5. And for the pairs of unit which are having more than distance 1, say distance 2 maximum, because it is 5, so maximum distance can be 5 upon 2 and the absolute value, so it is 2. So it is that will be 2 by 5. So that's why the increasing the distance between the units will give the more inclusion probability to the pairs of unit. That is the main property of this plan. This is an example. So similarly, now for estimation, we consider the Hurwitz-Thompson estimator, which is given by this, as you all know, and the Yates-Grundy form of the variance of this estimator under this plan is given by this expression, and the derivations are not, of course, shown here, but this is the expression, and for different choices of this distance function, that will lead to particular expressions. Now, an unbiased variance estimator, which was not possible for the BSA plans, is given under this plan. This is the expression for the variance estimator of the Hurwitz-Thompson estimator under the DBSP plans. This is an expression, and clearly with the suitable choices of the distance function Fij, an unbiased estimator will always exist. You have to simply select the distance function such that the pi ij's do not become 0. Okay, this is the estimation procedure. Now, depending on the choice of the Fij, because we can obtain different kind of sampling plans, so we have considered two particular cases in that time, that 2-point DBSP, we only consider two distances by taking value f1 and f2, and similarly for 3-point up to certain distance m1, we take the value f1. For distance between m1 to m to f2, and more than m2 distance, we consider the distance, the function f3, and these are of course non-decreasing. So based on this choice, we consider the two particular classes. Now for sample size, sample size 2, we have proved that a DBSP plan will always exist for the sample size 2. And the plan is simply given by taking the probability of selection equal to pi j, which is given by that expression. So we can always find a sampling plan for this sample size 2. For example, if we have a capital N is equal to 8, the population size, and then pi j is these are the choices of the pi j's for the, and the probability of selection, then accordingly from the values of pi j you just put it, because total will be number of possibilities are 64, so we can accordingly arrange. Okay, so this is always available for sample size 2, this plan. This is the advantage. Now, establishing the existence of the plans for sample size 3 or more is not that much, it is not so trivial. The class of, the properties of block designs can be used here. So we have used properties of a combinatorial properties of block designs. We have introduced one new class of designs, a distance balance sampling design. I'm just finishing. So we will not go into that, but this can be utilized. But there are a lot of research scope here for the existence of this sampling plan, because we have not yet established any sampling scheme for this particular plan. So that is the open area of research. So these designs can be obtained by, using two methods. One is method of symmetrically repeated differences and algorithmic approaches based on linear programming, but because of time constraint, I will not be able to show this. What happened? This is okay here. Okay, here it is showing, but I don't know. Okay, so now we consider the illustration with the data, how these plans can be effectively giving the better estimate. It is creating problem. I don't know. It is showing here, but that display is going on. No, because I have to show it. The variance results. Yeah, it has come. Okay, so we considered one real data set from a website taken. This is for average soil temperature, though of a particular month, taken at 4-inch depth, and that is available. And that web page had 21 variables. One of them is soil temperature, and we considered the estimation of, say, a monthly average temperature using, say, only taking sample of, say, 2 days or 3 days or 4 days measurement. Instead of taking all the 30 days measurement, we tried to estimate the average soil temperature by taking only sample of 2, 3, 4. And under this sampling plan, if you compare, you can see that we have 3 sampling plans here: simple random sampling, balanced sampling plan excluding contiguous unit, and the DBSP plan. So you can see under sampling sample size 2, the variance is quite low for compared to the simple random sampling and compared to the BSEC instead for all the 3 scenarios. So it is effectively, it will give the quite better estimator if you see the variance. It is giving quite less variance compared to the alternative sampling plan. So under these scenarios, when you assume that the population units will give, nearer units will give the similar measurements, these plans will be quite useful for alternative sampling plans. So that is the plus point for this. And now to conclude, I will say that there are a lot of scope of research for existence and construction of these plans, as well as there is scope for extending these plans to 2 dimensions, and maybe a sampling scheme may be developed to facilitate unit by unit drawing mechanism, and real distances between units, that may be also one interesting area of research. We have here right now considered the units between here and 1 and then 2 like that, but real distance between the units can also be taken as a actual scenario to further consider this kind of plan. Okay, thank you very much. That was what I have to say. These are the references.
Thank you, Dr. Baidyanath Mandan.
Yeah.
Now I'll request the last speaker for the session, Dr. Gloria Solano. She is from Joint Research Center of European Commission, Spain. She will be speaking on post-sampling crowdsourced data to allow reliable statistical inference, the case of food market prices in Nigeria.
So, good morning, everybody. This presentation is about how to post-sample crowdsourced prices that have been collected from voluntary citizens without following any sample design to allow for statistical inference. I will present here the results of the project Fruit Price Crowdsourced in Africa implemented in Nigeria. This project is the result of a joint collaboration with several institutions and several authors. We collaborated with the International Institute for Tropical Agriculture, with the Joint Research Center of the European Commission, Wageningen University and Research, and the Catholic University of Milan. My name is Gloria Solano, and I work at the Joint Research Center of the European Commission in the Unit Economics of Agriculture. The Joint Research Center is the service for science and knowledge production and supports the policy making of the European Commission, and we are in the site in Seville. So this is the outline of my presentation. First, I will provide you with the motivation. Then I will explain you how we use spatial statistical methods in this project. Then I will show you some of the results, and finally I will provide you with some conclusions. So the motivation for this project was the need for timely and reliable data on food prices. And for that reason, we wanted to explore how crowdsourcing based on voluntary citizens' contributions can help to provide timely and geolocated data on food prices by using a smartphone app in their return visits to the market. So it can be also considered citizen science, since citizens are contributing to the scientific production process. The idea was to integrate ICT tools, citizens, and scientific knowledge to produce near real-time information and geolocated to make available those data accessible, accurate, and actionable for better decision-making along the food chain from farmers up to consumers, but also to influence national and regional policies with regard to food security and markets policies. But we realized that dealing with large amounts of citizen-driven data can be very time-consuming and can be costly. It can be costly if we really need to keep the sustained data flow from voluntary citizens, especially if we are paying a financial reward to them. And in this presentation, I will not speak about this part, but I have another presentation in the afternoon where they deal with the sustained data flow. But here, I'm referring to how to treat this data, how to find the quality methods and the tools that can make this data more usable and trusted. And that is what we would like to do with this project. We wanted to explore how to increase the usability and the trust of mobile-based crowdsourcing data. Initially, we set up a web platform and an app to collect the digital contributions from citizens. But this is necessary, but it's not sufficient to ensure the quality of contributions. We also develop a web dashboard where the information is regularly updated, and this is also essential to provide final data to the data users to reduce search scores and information overload. But we realize that we need some statistical methods and tools to deal with this large amount of data from alternative data sources like crowdsourcing, and that's why we decided to use spatial methods and several algorithms with R that can help to improve the efficiency and validation of this citizen-driven data. And finally, that's why this is our research question, how to ensure the quality of those citizen data and what is the quality of them, so to provide a kind of measurement of the quality. This is our research methodology. We use the data collected in this project, the Food Price Crowdsourcing Africa project. We use spatial statistics with R and a web dashboard for timely and reliable dissemination of information from citizens for citizens. And we also provide some measurement of the quality and some results of the data collection. These are our data. We collected data for 8 food commodities in 7 different market types in 2 states in northern Nigeria. We had around 800 registered volunteers. Most of them were between 20 and 35 years old. 35% were declared as final consumers, while 41% were declared as farmers. And in average, all of them had about 4 years experience with the smartphone use. In the period project, we got about more than 23,000 submissions, which translated in more than 200,000 price observations. In the period from September to June 2019, we had a financial reward on, and from then up to now, the platform is running with any kind of financial reward. This is an example of the sites of data collection in the space. We can see also the spatial, in the map in the middle, we can see the spatial representation of data. But it was clear we need to deal with quality in crowdsourcing. We need to deal with errors in observations which are at point level. This is what we call our non-sampling error because of possible wrong interpretations of the users, locational errors, or possible fraudulent activities. And for that, we propose a data cleaning phase by using some spatial clustering methods and outlier detection. But we also need to deal with the sampling error. This is the error in the data set at aggregate level, which is connatural to crowdsourcing and web data because they lack of a proper sample design, and it can be considered more as a convenience sampling. And of course, we have self-selection bias of the participants. In the pre-processing phase, this is for the cleaning of the data. We develop some functions in R that have to be run sequentially, and each of them produce a different level of quality. So we need to retrieve automatically the data from the web platform through the API GET request. We transform the data to get some standardization of some variables like the units of measurement. We also geolocate each observation has the coordinates, so latitude and longitude, that they need to be allocated to the administrative subdivision of the area of interest. And finally, we use the outlier detection methods, which I'll explain now. How do we deal with the possible errors in the data? So we use a spatial cluster algorithm, DB-scan, that packs together the points that are close in the space. We need this because we don't have any detailed information, so official or a reference data source that we can compare, to which we can compare our data. So we need to define this spatio-temporal market, so to use the wisdom of this crowd by excluding those data that are very different to the neighbors. It works like we show in this tree. We run this DB-scan for spatial clustering. Some points enter a cluster, then we can discard them or keep them if they are detected as an outlier. And some points remain first isolated. Then we check if they are similar to if the value is similar to other clusters in the neighborhood. Then we keep and we relocate, otherwise we discard. This is an example of the result of this process. We see the different clusters in the space in different colors, and we see these crosses represent the isolated points that could not be allocated in the first stage. But after running the relocation, we see that some of the points can be relocated together with other clusters in the space, so we can run the outlier detection algorithm within each cluster. So once we have cleaned the data, we have cleaned the non-sampling error, we need to deal with the sampling error, and for that we run what we call the post-sampling to allow for statistical inference. To understand what is this, we can look at the graph in the right side. In the horizontal axis, we can see the population numbers of the different locations, and in the vertical axis, we can see the actual crowdsourced data. By putting in relation these two measures, we can find locations for which data are overrepresented in blue, or locations for which data are underrepresented in red in the graph. So we need to correct for this, and for that we run these 3 steps. First, we consider the map of, for example, n crowdsourced price observations, and we count the number of observations in each location, and we just run a simple average within each location. Then in the step 2, we need to consider a map of points and of locations as selected by a formal sample design, and we can use 2 different formal sample design, the simple random stratify proportional to the population numbers or the optimal spatial sampling. So we can define some weights that you can use to produce the estimate of the price at the state level by dividing the number of actual observations by the number of observations as selected by the formal sample design. And by reweighting the observations like this, our sample of observations will resemble a formal sample design. And I would like to mention that this we can run at different levels of aggregation. We can run this at a weekly basis, at a monthly basis, and we can run it only for different geographic aggregation, for state level, province, etc. And it will depend on the number of observations that we have available. We also created this indicator for the reliability of this post-sampling here, where it's an indicator that moves from 0 to 1. Is all actual collected observations in all locations are the same as the number of observations as defined by a formal sample, then the indicator is 1 and we have the highest reliability possible. If the indicator is 0, it would mean that all points are misplaced according to a formal sample design. I would like to present some results of this exercise. I will go a bit fast now. This is the quality in terms of number of submissions. We see that both states develop more or less the same. We see that during the period we pay financial incentive and have in place some behavioral tools. We achieve for week 20 more or less around 4,000 weekly submissions. But after we remove the incentive, the contributions go close to zero, and they start again when we set a new incentive in the second wave. With regard to the prices, we see, for example, here the price of local rice for the state of Kano. We see the development in time. In the left side, in the right side, we see the same information, but on the space, we can see by the level, by the intensity of the color, the different level of prices for these commodities. Here there is already some indication about the quality of the data. We see that more or less half of the provinces are covered with actual collected crowdsourced data. And then we want to measure to what extent these crowdsourced data are timely, accurate, consistent, and accessible in a cost-efficient manner. And for that, you use the quality dimensions of the statistical quality frameworks, and we develop some indicators and we measure them. So actually, I forgot to say that our idea was to have some kind of quality labels that provide us with an idea of the quality of a certain crowdsourced data set. Here, if we see the data completeness, where I was referring before, if we see, we calculate this as the number of complete weeks divided by the number of total weeks of the collection. We see that by provinces, more or less about 40% of the provinces have a good coverage. If we look in the graph below, this is the regional completeness. We see that in both states, more or less 40% of all provinces are always covered. This is what I wanted to show you here in this graph. If we look at the accuracy at the row level and the aggregate level for two commodities, for local rice and for white beans, I choose these two, but we also have, it's very similar in the other commodities. The outliers in the raw data are all around 2% and 4-5%. So it's a quite good measure for outliers. If we look at the aggregate level with this CSR indicator, we see that, for example, in the state of Katsina, we have a worse representativeness compared to the state of Kano. If we look at the external consistency, we triangulate with the data from the National Bureau of Statistics of Nigeria. Again, I present these two commodities, rice local and white beans in the two states. We aggregate our data at monthly level and state level, so we are able to compare with the National Statistical Office, and we do a ratio by dividing our actual price, our crowdsourced price, by the price of the National Bureau of Statistics. And we see that the relation is quite stable for both commodities in both states. And they are around 1 for rice local, both in Kano and Katsina, and also for white beans in Kano. But we see that for white beans in Katsina, our prices are consistently lower than the prices from the Statistical Office. So here we could further investigate where is this difference coming from. With regard timeliness and accessibility to the data, we developed this web dashboard, which is accessible in the week link provided there. Unfortunately, I won't have time to show you how this works. It's a completely interactive dashboard, and it runs automatically twice a day when the algorithms in R are updated. They feed actually this web dashboard. Here we can see the time trends. We can see also some indicators on the average prices for the selected period. We can select the commodity. We can see also the indicator on the weekly price changes, and we could even compare the prices of this year on a certain week or month to the prices in the previous year. And as a proxy for access, we saw the number of visualizations in the first 3 months was 1,200 visualizations from about 200 volunteers from the 380 volunteers that were actually providing data. We also were interested in the measure of cost efficiency. That was, we calculated several indicators for that. Here I present 2. The first one is the cost per data point. We see that from week 30, more or less, the cost per data point is around 20 euro cents. And this is mainly calculated based on the financial rewards, because we consider that the initial setup investment was already done, and the remaining costs are mostly related to the financial reward to provide it to the citizens. We were also interested in knowing the time to submit data. How long does it take for the participants to use the application to submit the data? And here we see that in most of the participants took around 5 minutes. This is the median time. Then there was some 25 percentile where it took less than 5 minutes, and the 75 percentile that took more than 10 minutes to submit the data. And these are the conclusions. This is a pilot for real-time data collection on food prices from voluntary citizens. We consider it both was successful in terms of data quality and the quantity of data. We consider this quality method that we present here is scalable to other regions and expandable to other type of data and other fields. But for the application, it's clear that we need a large number of data collected, and it's very important to have the exact geolocation of each point. We consider that this method could be complementary to other data sources, like the official data sources for the spatial temporal analysis of the data, because this data offer more granularity in time and space. And we also have characteristics on the individuals that are providing data from citizens and from behaviors in time and space. And I wanted to mention, I didn't mention in the presentation, that anonymization of data and privacy is absolutely ensured during the data collection and processing process. So thank you very much. If you want some more information, we are still finalizing a report on the whole explanation of this project.
Thank you, Dr. Gloria. Let us thank all the speakers once again before taking the questions. Now we open the presentations for discussion. Questions or clarifications, if any, to the speakers. Questions to the speakers? Yeah. Please identify yourself and the questions, which speaker you are referring to.
I am Dr. Paneer Selvam, scientist from CIMET. My question to Dr. Anna Christian is about crop cutting. So when you do crop cutting, so you also, when you do crop cutting, you also measure the moisture content in the grain. So how you measure and how you report the actual grain?
I am Dr. S.K. Hejama, ASRI. To the last speaker, she mentioned that outliers around 5%, but data cleaning are excluded. If you don't exclude them, then what happens to the efficiency and the quality? It suffers too much or quality effect if you don't ignore the outliers and include them. How much is the quality effect and all that?
So, one more question. Actually, I want to ask Dr. V.K. Segal. So, I'm curious about the low burning villages. What is the reason? Do you have any reason for the low burning villages?
Okay, if no, then I'll ask the speakers to respond. First, let Dr. Anna respond to the question on moisture content.
So, sir, we provided the implementing agencies with moisture meters. So after the drying process, so for the case of the Philippines and Thailand, the standard moisture content is at 14%. But for Lao PDR, according to them, they sell their harvest at 15%. So we provided them moisture meters to to measure the moisture content of the samples.
Thank you, Anna. Now I'll request Dr. Sehgal to respond to the question of reasons for low burning villages.
Thank you for the question. Actually, though I am not the person who looked into that, only identified the villages. But the ground reports which came to us from the State Department officials, one of the major reason is they plant generally shorter duration varieties, so they have time, so there is no burning. Whereas like Pusa 44, which are longer, 135, 140 days varieties, there the problem is very severe. So one of the major reasons relates to that. Another is related to availability of technology and IEC activities, but proportionately, how much is each one of it is contributing, I can't say. The data is not there.
Thank you, Dr. V.K. Sehgal. Now I'll request Dr. Gloria to respond to the question on if we do not exclude outliers, what will be the effect on the quality?
So this is it's open? Yes.
Yeah.
This is a very good question. Thank you for the question. We tested that, so at an aggregate level, the effect on the quality is low because we have many data and the percentage of outliers is low. But because we disseminate the data as a very low level of aggregation in the space, we prefer to discard the outliers.
Yes.
Can I ask one related question to that?
Yes, please.
How do you detect outliers and how do you know whether they are influential or not?
If they are influential or not. So we assume that outliers at least are.
First, how do you detect outliers?
So this is more, what I explain is that we create these spatio-temporal clusters where we use a spatial clustering algorithm. So we consider that prices that are close in the space based on the law of one price that will be very similar. So we build these clusters. Each time we run the algorithms, which we do actually at a daily basis. So every day we have different data because we aggregate for the last 7 days. We run this clustering algorithm. And then within the cluster, we run the outlier detection method. And you are asking which method do you use for the outlier detection? Then,
They may be the actual realizations.
no, because in prices within a certain space, for the same commodity, for the same market type, because we do also for different markets types separately, it's not possible that a price is very different to the rest of the neighbor prices. That we consider any price that is very different, we discard. Yeah. We use DB scan with R. So this is we need to define the threshold distance, and we need to define the minimal number of points we consider to build a cluster. Yes.
It is K-means clustering?
Sorry?
It is K-means clustering?
No, it's not.
You're doing on the basis of the mean and then on the number of clusters. It has to be non-hierarchical.
Okay.
Yeah, anyhow. Yeah. Any more? Yeah.
My question with Dr. Anna.
Please identify yourself first.
Myself, Dr. R.K. Yogi from Indian Council of Agriculture Research. I am working as a scientist at Ranchi Center. You mentioned that you are in this estimation of this comparison of your methodology with the official data. So in last slide, you mentioned that these estimations are influenced by the local leadership components. So how this is affecting this estimation data? Discussion.
Sir, so yes, part of the methodology is to compare the estimates using the 3 methods we have for area estimation versus the administrative data. So we found out during the dissemination workshop that we conducted that actually some of the, well, particularly for the pilot provinces, instead of the actual, say, yield or area estimate, they are reporting the target. So that's why it's surprisingly higher than what we are getting based from crop cutting and from the whatever area estimates that we're using. So that's the problem with admin data. It's one of the issues that we've identified.
Okay, thank you very much. Any more questions? No. Okay, if not, because we are already, is there any? Yeah.
Yeah, take one.
One question only.
Please identify yourself.
I'm Neza. I'm an MTech graduate in Machine Learning and Intelligence Systems Congratulations. I'm from Bangalore. I just had a follow-up with you, ma'am. No, the lady. Yeah.
Gloria,
Sorry.
yeah.
Yeah. So the outlier. Can you hear me? Can you hear me?
No, your mic is.
I'm not sure about the rest.
Okay. Yeah. So the outliers, you said you're doing the clustering algorithm based on the nearest distance, right? So the outliers, you're saying you're plotting it in a scatter plot and checking where the data points are, you know, how far they are from the maximum points, or how are you, like Sir said, how are you detecting the outliers from the nearest cluster of data?
So in principle, in this algorithm, the only thing we need to enter is to say what is the threshold distance we from each point to the rest. And then it's based on the threshold distance that brings together the points that are close in the space relative to this distance we fix. And we also need to say how many points we considered for this.
On what basis are you selecting the threshold?
It was for us like we did validation, parameter validation. We were testing, yeah, we can do, we can do also later, yeah.
Yeah, okay. So thank you for all the questions and the answers by the speakers. I would like to thank all the speakers for their very nice presentations. I think this was a very quite interesting session, and we'd like to thank each one of you for being in this present in this session, and we would like to thank the organizer for giving us an opportunity to organize this session. I would also like to thank the chair, Dr. Rajendra Prasad, for conducting the session very nicely. Thank you very much.
Thank you, sir.
Thank you very much. We would also like to thank
Now
the co-organizer of the session.
There is a training session on food insecurity experience scale in hall number 4, and today the lunch will be available in the swimming pool lawn from 1:30 p.m. Thank you.
Same.
No, this.
May I request all the speakers to come here, please, for a photograph? All the speakers. May I request all the speakers to come here, please?